today's grand round. We will have one of our sleep fellows, Sam Hole, to present to us. So Sam was from medical school, was from Louisiana State, and then he did his residency in Louisiana State as well, and decided to have a one-year stopover up here north in Cleveland. Then he's now slated to go back to Louisiana State, Shreveport area, to start his job after the fellowship is completed. And his wife is also joining a sleep fellowship down in Shreveport, Louisiana.
Conflict of interest.
Sorry?
Conflict.
Well, I mean, today he's gonna talk about AI and sleep. So why don't we just hand over the podium over to Sam? All right.
All right, thank you. All right. Hello, everyone. Thank you for the kind introduction. Let me just pull up these slides. All right, can you guys see the slides?
Yeah.
All right. So as I said, today I'm going to give you guys a talk about artificial intelligence and sleep medicine. I wanted to give this talk partially out of my own self-interest in terms of just becoming very interested in artificial intelligence, and I think it's going to be a very relevant topic, especially in the coming decades, I believe. So just going forward, I have no financial disclosures related to the topic of this grand round presentation. And here are some of the learning objectives. So just a word of warning, we're becoming a lot of material. So if it looks like there's fire coming out from behind me, it's because there is. So the learning objectives are to develop a historical understanding of artificial intelligence, develop an appreciation of utility offered by artificial intelligence in an age of big data, develop our knowledge of the basic framework of artificial intelligence, machine learning, and deep learning, develop an appreciation for the developing area of sleep medicine, where artificial intelligence may play a role, such as with ESGs, consumer sleep technology, and in clinical practice, and developing an awareness of considerations required for the proper implementation of artificial intelligence in clinical practice. So to start off the talk about artificial intelligence, we kind of need to define what intelligence is. It's a little bit of a gray area of definitions. According to the Oxford Dictionary, it's the ability to acquire and apply knowledge and skills. I know that many people would argue there are many other definitions that you may use, but that one's particularly good for our talk at hand. We as people tend to value intelligence. We even call ourselves the wise man. So now that we kind of have a rough definition of what intelligence is, what is artificial intelligence? So according to the Oxford Dictionary, it's the theory and the development of computer systems able to perform tasks that normally require human intelligence. And they give some examples. That's an okay definition, but really it kind of leaves you wanting because it doesn't really say too much. So when thinking about artificial intelligence, we really have to start thinking about it in really two different dimensions. You can think about it from more of a cognitive approach, which is like, is it artificial intelligence because it acts human, or is it artificial intelligence because it does the things that humans would do? So that would be more of the rationalist approach. So the cognitive approach is sort of the mingling of sort of the psychology versus sort of the mathematical computer sciences, where from the cognitive approach, does it act human? Does it seem human? And sort of way you can think about rationalist is, from a loose definition, is doing the right thing. And now what I want to do is start moving towards, just thinking about it in terms of history, but keeping those two dimensions in mind. So if we want to really take it back to the beginning, we can go as far back as Aristotle in order to think, because he's sort of credited as sort of the father of the field of logic. And it was sort of the first time it was sort of codified right thinking. So say, for example, one of the famous syllogisms, Socrates is a man, all men are mortal, and Socrates is immortal. It just sort of codified. That That famous one is actually probably credited more towards Sextus Empiricus as opposed to Aristotle, but it's just sort of shows how we can take something that has a structure and then try and make it have the right thinking. But now moving just a couple years forward, right? In the 1950s, there was a guy named Alan Turing who in his paper, Computing Machinery and Intelligence, was published back in 1950, where he sort of presented a thought experiment called the Turing test, where essentially if text is presented to a person and that person can't determine whether or not the text was created by a machine or by a human, then it would essentially pass the Turing test. And at this point, there have been no computers that have actually been able to pass the Turing test. But it's very interesting that the idea even came about in the 1950s. Unfortunately, even though they had the idea, doesn't mean that it was able to come to fruition, partially because of the lack of computing power. Computers were also very expensive, and research with this would be sort of complicated because of the requirement of resources. So what you kind of see in history is that the interest in AI actually sort of ebbs and flows over time. And part of that may be a consequence of the lack of computational power. But in 1952, the term machine learning was actually coined by Arthur Samuel over at IBM. And then in 1956, there was the Dartmouth Summer Research Project on Artificial Intelligence, which was dubbed by the AI community as the conference that started it all. It was actually during this research project that the program, the logic theorist, was actually presented, which is credited as being possibly the very first artificial intelligence program presented. And during that conference, artificial intelligence was actually coined as a term. But in the 1950s to the 1980s, we start to see sort of the ebbing and flowing of interest in the AI field, because a lot of it is just computers just haven't quite caught up yet. Essentially, they had to wait for Moore's law to take place. And Moore's law is simply put, your microchips are going to double in size roughly every 2 years. And it's only really been recently that we start to see it start to trail off from that trend. So moving forward, as Moore's law just kept on progressing, we got to see deep learning finally showed up in 1986. And not too long after that, you start to see some more development in terms of, IBM's Deep Blue artificial intelligence program defeated the world champion at chess. And, Dragon Dictation came available in 1997. And even thinking about games, 2017, Google's AlphaGo actually defeated the Chinese Go champion. So, what other game might they win at except Jeopardy, right? So in 2011, the IBM program Watson actually challenged people on Jeopardy and beat them. And the person who's displayed on the left is actually the person who had the longest streaks of victories on Jeopardy, and the person on the right had the highest earnings on Jeopardy to that point. And so he ended up actually defeating them both. But the sort of, I don't know what you call that, a floating Calvarium in front of you, it's not the actual computer itself. That's just simply a representation of that. This is actually the picture of the actual computer. And it was too big, too hot, and too noisy, life goals, to actually make it onto Jeopardy. So they had to just sort of have a representation. But one of the big things to look at is just how huge it's like the size of a room. We always joke about having a calculator that was the size of a room in the past, but now they just beat Jeopardy. But the big thing is that Watson wasn't actually hooked up to the internet. For one, that would have disqualified him, but number two, he couldn't actually search the information fast enough in order to generate an answer. And so they ended up having to create a giant database approximating to about 200 million pages of information that he can just call on the spot. And that's really just sort of an interesting concept because that is so much information that most of us just don't have that available to us just at the drop of a hat. And it brings us to one of the big topics in terms of artificial intelligence, which is big data. And so Oxford defines it as a set of information that are too large or too complex to handle, analyze, or use with standard methods. And then IBM, the tech giant, also has their own little definition, is a data set whose size or type is beyond the ability of traditional relational databases to capture, manage, and process the data with low latency. And they give three major characteristics for it. They call it the 3 V's: high volume, velocity, and variety. And one of the things, the reasons why big data, I think it's so important, is that in many ways you can think of artificial intelligence as sort of being a natural consequence of big data. And we'll discuss this more in going forward. But I want to switch gears and big data can come from can come in many varieties, whether that's more of a structured variety like tables, numbers, and such, or as unstructured data, whether that's music files, videos, or from our standpoint, PSG data. So we're going to shift gears for a second and just talk a little bit more about the different types of artificial intelligence, because we sort of discussed it from more of a larger grand picture. But I wanted to talk about machine learning specifically and deep learning, because those ones are really sort of the key ones that seem to be popping up very frequently. And machine learning is defined by the Oxford Dictionary as the use and development of computer systems that are able to learn, adapt without following explicit instructions, by using algorithms and statistical models to analyze and draw inferences from patterns and data. So one of the big key takeaways I want you guys to take from this slide is that our machine learning is a subset of artificial intelligence, and deep learning is a subset of machine learning. The big key that really defines deep learning from machine learning is the use of neural networks. Artificial neural networks. And that's something that we're going to go over in a little bit, but I just wanted to prime you guys first. So this slide kind of gives an illustration of what is the process of a machine learning. So essentially you feed it some data, which you can see on the left, and then you have some sort of feature extraction, oftentimes done by a person. And then it's sort of fed into the algorithm, which then does some sort of classifying and then spits out an answer. And so the type of learning that machine learning can do can follow some different types of categories, either supervised, kind of like if you have a person who's feeding in information, making sure that answers are correct. You have unsupervised, where essentially the machine does itself, or reinforcement. Say, for example, if it's learning to drive a little car and it's running into something, it's being reinforced. It's not necessarily a human that's enforcing the rules. Deep learning is a little bit different from just the broader category of machine learning, because it uses that neural network that we were talking about and basically puts together the classification part and the feature extraction into the computer just doing it on its own through this neural network. And that's really one of the big differences. And so one of the advantages of this is that, for one, it kind of can eliminate some of the human requirements for it and just sort of eliminates a step. But because of that, it can also be very helpful in being used on very large data sets, especially in an age of big data. So this is kind of a picture sort of illustrating sort of what we're talking about also. If you have a car, the same stimulus, the machine learning would require have all that feature extraction and then have to do the classification, and then you get, it's a car. Where deep learning, it happens within this little neural network. So what is this neural network? There are three main parts of it. There's the input, what they're called the hidden layers, and the output layers. As you can see in the hidden layers, there are many layers. And because there are many layers, it's called deep learning, because of the number of layers that are in there. So usually with deep learning, they use what's called a feed-forward multi-layered neural network, where essentially it's saying the information always goes from input to output in one direction. It doesn't go backwards. And so the way I think about neural networks is it's a weighty matter. And so the way it works is kind of like neurons. Each of these dots, even on the previous slide, each dot is considered to be a node. And the node will essentially send out a certain signal, which is of a certain weight. And if the next node gets a high enough threshold, it fires. And depending on the weight can determine whether it causes the next node to fire. So it's like a progression of neurons, sort of reaching some sort of action potential threshold. And the way the system works is by using a loss function, which is in very general terms, just a program that's supposed to make your algorithm match your data. Try and get it as close as possible. And it does this through error backpropagation, where it essentially works backwards and redistributes the weights so that whenever information flows back through it, it's more likely to get closer and closer to the actual data set. And so what we inside of this machine learning process, you essentially have, and this sort of repetition, you have some sort of data preparation cycle, which you can kind of see as the first 3 squares on the left. And then once the data is prepared, it then goes into the actual learning process where it just kind of gets tested on held out data sets over and over again until you get as close an algorithm as you can get. And then once you get your algorithm, you then test it against another untested data set in order to get the performance metrics and the model generalizability, how well your model then can be generalized to all the other information that's out there. And so this is all very interesting, and it's much more complex than I'm talking about, but this is just the basic general overview. We know that it can be very helpful, and we are already starting to see some artificial intelligence show up in our daily lives, such as with Tesla's driving cars, we have facial recognition, or RankBrain, which is the Google AI that help us search things. But we're also seeing it starting to move into medicine. So there are some research where they're using it to try and analyze chest x-rays. We also have the FDA actually just approved in 2018 some AI for looking at diabetic retinopathy. And the cool thing about it was it was meant for use without further physician interpretation. There are also a number of other ones, and I'm not going to go through this entire list. It's just to show that there is a lot in medicine. But sleep medicine has actually really been looking at this field pretty closely. And there's this really nice page on the ASM's website that roughly, essentially the rest of this presentation is roughly just a condensing of a lot of the materials from this website. If you really want to learn more about it, I would say click on this link as the one that's in the box, because that one's really going to be your high yield. But here's sort of some quotes from that article itself, actually. And I think that it really just sums up the large view of the ASM. So it says, the sleep medicine is well positioned to benefit from advances that use big data, to create artificially intelligent computer programs to analyze the massive quantity of physiological signals acquired during PSG. And then the next one is, AI has the potential to deepen our understanding of sleep disorders, improve patient-cared sleep care, augment day-to-day clinical operations, and increase our knowledge of the role of sleep and health at a population level. And this part is really key. But the benefit of AI will ultimately hinge upon whether it is appropriately and responsibly used. This really sums up a lot of the talk, but repetition is the key to learning. So we're going to keep on moving. So one of the
cheap terms there that I focus appropriately and responsible. That's a perspective.
And that's
So who's the judge, jury? We don't have three. We don't have three parts of our government on this particular state.
That's true.
We don't have judge. We don't have legislature. Exactly.
It's true. And so there's a lot of
That's very informal as well.
it's true.
So that's all I want to say on that.
Well, we have patients, doctors, and insurance companies.
That's right. But the goal of artificial intelligence and this is also quotes from that article, the goal of AI integration should be to augment, not replace, expert evaluation of sleep data. And ultimately, the clinician, not the computer software, is responsible for the patient diagnosis. The AI may help, though, for streamlining clinical operations by analyzing big data for wearables, PSGs, and the hope would be with more time, you can have a face-to-face interaction with the patients, and then maybe with better tools, you can increase the precision in the evaluation of sleep disorders. But like you were saying here, a lot of the technology is sort of in its infancy. And so some of this may come across as sort of speculation to some degree, because we don't really know where the future is going to lead, but we have some hunches of where it's going to lead. And so one of the goals is that, as we said, just this massive amount of data that we're all trying to focus down into our patient care, which medicine is starting to try and peek towards personalized sleep medicine. And so how can we do that unless we can somehow pull all this information together? And artificial intelligence, one of its goals is to hopefully be able to help us do this. So just a fair warning, one of the things that I'm about to go through just a lot of different examples of artificial intelligence in sleep medicine is going to be sort of a show and tell kind of thing. So we're going to be moving from example to example relatively quickly. So just be aware. But just moving forward, in terms of talking about automated scoring, in terms of PSGs, it's not a new thing. There have been computer programs since the late 1990s that have actually shown comparable to human inter-rater reliability. But one of the big problems from that time period was that the program was built and did a good job with people who were healthy. It was a healthy population, but in a small population at that. It didn't really work well for people who had more comorbidities like heart disease, lung disease, and that kind of stuff. But also you lack computational power. Most people didn't have access to anything that had the ability to do this. And nowadays we do have more PSG systems, but the key thing about this is, we have PSG systems, but also we have a couple named on the bottom where they can actually auto score. Enso data didn't make it on the list, but that's one of them. But AI actually, how do we know that whether this technology is doing well or not? And part of that is using kappa values. And the one that's sort of been used traditionally as sort of the benchmark is about 0.68 to 0.76. The ASM's ISRs boast an overall interscore agreement of about 82.6%. But we've actually had some AI programs in a meta-analysis that showed had ISR of about 85%, and another one showed that contained over 1,000 subjects, a kappa value of about 0.8. So it's getting there. It's really kind of moving in the right direction. But it's not only just used for auto scoring in the sense, we also can work hand in hand with this technology. And it's been shown that whenever you use artificial intelligence with sleep technologists, you actually can increase the interscore reliability too. Now, one of the hopes and dreams of AI is not only to just score it, but also try and incorporate more aspects of the PSG into the process of scoring, or just understanding the PSG in terms of also using the heart rate variability and even respiratory dynamics. There have actually been some novel parameters. And so one of the keys that a goal of it is sort of phenotyping. We all know that there are some different phenotypes out there, but it's not necessarily very well classified at this point. And one of the thoughts is maybe AI, by incorporating a lot of things together, may help us be able to do that. And so there are some novel PSG parameters, such as with respiratory event length EEG changes that better predict sleepiness than AHI and have been shown to decrease with PAP therapy. Another example is in cardiopulmonary coupling. They've found what they think to be a distinct subtype, where if a person has more events during non-REM episodes, then they may be more likely to suboptimally respond to PAP therapy and may in the future have some sort of usage and anticipatory guidance of how this patient might respond. as I said, well, some of this is just sort of speculative, and you kind of have to keep, take these things with a grain of salt. So moving forward, in terms of respiratory scoring, not just the basic scoring, it has been shown to be similar to the neural scores, and we look at a deep neural network, deep learning, using over 10,000 PSGs, it was able to get an R-squared value of 0.85, and for automated limb movement scoring, about 0.79, which is pretty cool. Let's see, there we go. And this is actually, I think, one of the coolest things that we're going to talk about here is that AI may also be useful in the diagnosis of narcolepsy. We all know that MSLTs has a poor retest probability, reliability, and using AI, there's a group that used linear dimension analysis and deep learning in order to create what they call a hypnodensity chart, which we'll look at in just a second. But it actually was able to confirm narcolepsy with accuracy similar to traditional PSGs followed by MSLT. And this is what a hypnodensity looks like. A hypnodensity is basically just a representation of the probability of each sleep stage of each epoch. And it was actually shown to have good sensitivity, as you can see on the graph on the right. But you can sort of see the sort of a fingerprint of narcolepsy. And we're going to look at that hypnodensity again on the next slide. But this pattern actually has been really well shown for narcolepsy type 1, but not so well for narcolepsy type 2. A part of that may be because of the squishiness between narcolepsy 2 and some other idiopathic hypersomnia.
Because somebody has to figure out, those two are different, and the neural networks in your brain have decided that those are two different conditions.
Right. And and we'll talk about some of those limitations of AI later. But what we can see here is a hypnodensity chart. And on the left, you can see white represents awake, red is N1, light blue is N2, and the dark blue is N3, and black is REM. And so the person on the top, you can kind of see the person starts from awake, starts going into micro sleeps, goes into N2, N3, and then you can just kind of see how REM becomes more and more likely to be scored. But if you look at the bottom, which shows a narcoleptic patient, I mean, of course, it's showing a REM at the very beginning, which is pretty characteristic, but then also you can just see how it's just different. You can see how, even though there are some REMs, it's unique. And because of this uniqueness, that's what they were talking about as being relatively well diagnostic of narcolepsy, type 1 specifically, which I thought was very cool. But this is an example where AI isn't necessarily just used for taking over our jobs, but may add another tool in our arsenal in order to have better care for our patients. Now, let's move forward and talk a little bit about consumer sleep technologies, or CSTs, as I might refer to them later. And we all know that CSTs are something that's becoming bigger and bigger. You can see here as the years progress, more and more people are buying and using CSTs. But the usage of these are not really well, defined in modern medicine. We don't really know exactly where it sits. And because part of it is, you're generating this massive amount of data. So, artificial intelligence may actually play a role in it at some point, but but we as providers can grab a person's phones, go through it as quickly as possible, but that's not summarizing it well enough for us. And we don't know how well characterized the data is. But there is some advantages to using consumer sleep technology in the sense that it may enhance the patient's awareness of their sleep. In some degree, it's not particularly expensive, and you can get more information over a longer period of time. So it may have a place in the future, but one of the big issues is that it's generating an overwhelming amount of data, and we can't necessarily put it all together. And so this is where AI may actually shine relatively well. And we do see that artificial intelligence is starting to grow in this field as well. And here's some examples of some of the technology that's starting to use some AI. Whether these ones will be the main ones on the market in the future is unsure, or how well it's going to pan out. it's also unclear. But we also see, there's some of the machine learning using heart rate variability from risk photopleth. I'm not going to try and pronounce that. It did get a kappa value of 0.55 and 0.42 for detecting the sleep wake differentials. And even some deep neural networks are being used with the Apple Watch to estimate sleep stage and sleep disordered breathing. So as it's not necessarily to say these things are, how long it's going to take for these things to really catch up, but these things are in the works. So as I said, we're going to start moving a little quick. So here's an example of where some wearables are being used to try and classify some different types of clusterings of insomnia. We also have an example of some AI being used.
Go back. We'll just up at 5 new insomnia activity clusters. Okay.
And
So there's correlations within that
Mhm.
big multi-layered neural network. All
Right.
right.
And so,
They have not recognized.
yeah,
And they've not recognized it because they're not actionable by anybody.
right. And so, and then in clinical practice, AI has actually been used to develop 3D printed masks, which is kind of interesting, but although that sounds like it'd be extremely more comfortable, actually, some people say it's more like a wetsuit, and a lot of people can't tolerate it because of that. And it's been used a little bit more in Singapore than other places, but hasn't really caught on too much so far. Other place where we can see AI starting to come about in clinical practice is in app download information. We're generating huge amounts of data, and so some people are trying to use it to have sort of a triggering for the provider to know if a person is starting to fall off the bandwagon. Whether I would like that in my clinical practice is questionable, but that's something that some people are working on. And here's another example of people who are using PAP adherence data with some machine learning, where they're actually, the MESAL program boasts that it can increase its use CPAP compliance by 1.14 hours per day. And there was apparently no significant difference in the costs found with using this. So that's what they were boasting.
That will be in the details.
Yeah, that's the big question. And here's another example where in clinical practice, people are trying to use AI in order to do some sort of behavioral therapy. Here's an example where people are trying to use deep learning to try and predict OSA from lateral x-rays.
Taken during weight.
Taken during wakefulness, that's correct. And here's another example where deep learning is being used to try and detect REM behavior disorder. And they claim to have an 80% classification accuracy. But here, one of the big points is they were just using the best single EEG channel. So neurologists may go crazy about what we looked at the paper. We couldn't really figure out exactly which specifically they were using. So that's also
Data from, you go back, a few minutes of eyes closed, resting. EEG. Okay.
So that was sort of an interesting one.
Well, you could, did they have insomnia controls? I mean, it's all in the control. You pick two and you find a difference. You go, oh, that's great. What's the confound?
Right.
Okay.
And here's an example where they use machine learning in order to dig through the European network database. And they were essentially finding clinical features of narcolepsy. I'm not really sure about the full utility of this, but at least it sort of shows machine learning being used in giant databases. So now moving forward, let's think about the challenges for AI implementation. This isn't just for basic clinical practice, but also from sort of a regulation standpoint as well. So some of the challenges can be sort of boiled down into data challenges, some of the ethics involved with it, some guidelines and research consensus, some of the regulations, and some concerns with tech aversion and trust from clinicians. So one of the major, in terms of starting with data, is we have to be very careful about protecting patient information. This is key because we need to make sure we ensure patient safety along the pathway. We can't sacrifice it for the ability to read sleep studies faster, for example. Some of the solutions that we use nowadays are like at-rest and in-transit encryption and minimum necessary access protocols. But that's just scraping the ice in terms of things that we're going to have to consider. Another issue that comes about with sort of as a barrier to using artificial intelligence is a lot of our data is siloed. That's not only so we're a lot like those grain silos right there, where all of us are sitting there with our big data sets, but it's not all in one place. It's all broken up into little outplots. And there are a couple of reasons for this. Partially, there's no real infrastructure at this point, and there's no real national data sharing initiative. But also it comes from the fact that even when we do have data, it's not all exported in the same data file type. It's not necessary, and the European data format is one of the more commonly used ones, but it's not actually officially standardized. And also, if you have your sleep study, it doesn't necessarily mean everybody's using the same vocabulary. So a computer, it can't understand that these different vocabularies are the same thing, at least at this point. And so when we do, a lot of the research that they use is actually coming from some better used data sets. And here's sort of a list of some of them. But if we consider the number of studies that are listed here, it's not very many in comparison to how many PSGs that we produce all the time. And even in these data sets, you can see sort of the age ranges that are being used, and some of them are healthy populations, some of them aren't. And all of those differences can lead us to have some bias, which can bring us to some ethical concerns. Because computers will just take what you give it, and it's going to just push it forward. And so the differences between, like, say, for example, we talked about PSGs that were being trained on healthy data sets, they're not going to be able to be used very well on unhealthy data sets because they lack generalizability. And some things that it's not even just humans that can cause bias. Also, it can be as simple as the difference between the electricity in the United States, which is 60 hertz, and Europe, which is 50 hertz. That can also cause some bias in the data that the machine will have to deal with. And also, some bias may come about simply for reasons that we don't have control over. Like if academic centers are contributing more data to these data sets, then you're probably going to have populations that are seen in academic centers are more likely to show up in your data set. These are all just examples of bias that can creep in. But one thing that machines will do also is just magnify whatever's there. So if there is some sort of, say, for example, a sex disparity between how people are judging these PSGs, it's just going to blow that up and make it even bigger. So one of the quotes from one of the AI talks that I really liked was from Emmanuel Minot, where it essentially said, AI cannot make data into high quality data. And that's very key. We have to keep that in mind moving forward. And one example that I really liked was that if you say, for example, are training a PSG system, a lot of the parts of the sleep going to be scored N2, N3, and REM, but you're not going to get quite as much N1. So
you don't get wakefulness either.
Yeah, and the example I was looking at didn't have wakefulness written down on this, but
because they don't think of it.
But then the N1 may not get as much data. And so even if you were trained on 100 PSGs, is it going to be biased against N1 because it just doesn't have enough data for it? So these are just examples.
Or you just say, is there information and when it would be important, whatever it is.
True.
Wakefulness is one, and there are examples.
Right. And so part of the problem is that in some ways, there's sort of a black box when it comes to AI, where you throw the information in and it spits back out, but we really don't know what happened in the middle. And other things is that, this is especially true for wearable technologies, where the algorithms and the data sets may be tested and trained using proprietary stuff, including data that's not publicly available or algorithms that we don't have access to look at to verify. And so there's also sort of this heterogeneity within the software. And so the ASM had some things to say about the transparency and disclosure is that manufacturers are expected to clearly delineate the intended population. And that would include things like demographic information and disease characteristics, specific specifications of techniques used to address artifacts, sampling weight filters, and a data dictionary. And of course, the obvious, it must show it to be comparable to expert scores. But one of the big takeaways that I really like from one of the ASM articles is that sleep laboratories should work, and this is in quotes, sleep laboratories should work with the product manufacturer to trial the software of interest in their own laboratories to determine real life performance, sort of a try before you buy kind of thing. And one of the reasons why this is so critical is because it's important for clinician buy-in. Because if you can't prove that it's good on your own data set, then you're less likely to get clinicians to be able to start using it. And this is where we kind of come to the idea of maybe some tech aversion, where, you know, a lot of times we sometimes shy away from these computers because many of us have bad experiences because it's not necessarily user friendly, or, you know, we don't necessarily have the IT support that we would hope to, whether that's them troubleshooting the software for us when we have troubles. Do the providers have enough training to actually know how to use the software? And does the software even work with the software we're currently using? And so with all of these things put together, a lot of times we can be hesitant to moving forward with using these technologies. But this is where it's going to be very important for us thinking forward that we have to be careful about how we implement it. Otherwise, we might worsen the tech aversion. So in terms of, and sometimes, you know, one of the reasons why we have hard time sometimes using this AI is because there's some lack of guidelines or research consensus. It's sort of what we talked about earlier, sir. There's lacking gold standards or ground truth for some physiological or clinical outcome. Like, for example, the narcolepsy type 2, where this is sort of a grayness where we as providers have a hard time parsing it out, and the computer is too, because we don't know whether to believe it or not. Another example is there's actually programs that are used to distinguish between two subtypes of RBD, where you can find REM sleep without atonium, but they're not really well used. And part of that is because what's the difference between the excessive transient type versus the sustained is not well defined. And so this is just kind of an example of that. Now, moving forward in terms of the regulations that kind of are regulations barriers for implementing AI would be, you know, like say, for example, FDA approval. The FDA actually does have a digital health innovation action plan to help foster technological advances and ensure patient safety. And they also have a digital health software pre-certification program, where they essentially can use this 30-point software review program to help figure out if a program meets qualifications. And if it does, it gets a pre-certification to help it move forward into implementation. Yeah. So the ASM has opinions. It says the FDA requirement for scoring accuracy is not very stringent. So in some ways, the ASM is sort of has some statements in terms of only software analyzing PSG data should be considered for implementation at this point. And the ASM is actually starting to work towards some ideas towards of artificial intelligence in terms of helping it with this implementation. And the two big programs for it are the Sleep ISR catalog and the Sleep ISR reporting reward program. So the catalog is sort of our version of big data, and the reward program is our big data builder. And we've actually seen a pretty good enthusiasm from amongst the sleep community of building.
What is the record rewards program?
We'll go into that.
And do you get, do you get a coffee maker?
You can even get Amazon cards. Pretty exciting stuff. And so the Sleep ISR catalog, and I'll just read it here. It says, until recently, the ASM has relied upon trusted but finite sources for compiling records that our gold standard panels. I might have made mark. Limited patient population. The record of reward program will infuse a more diversified archive of records to draw from, essentially enhancing a lot of good stuff. But then moving forward, and then talking about the Sleep ISR Record Reward Program. Essentially, the record rewards is the next step in the effort to grow the Sleep ISR. And the ISR is not just used for AI, it's using for big data and building the ISR itself. And it addresses two needs: diversifying the catalog of records available through Sleep ISR to improve competency of sleep scores, and providing a source for the comparison of manual to automated scoring as part of a pilot program to certify AI scoring software packages. So just as we had our little pre-certification for the FDA, we also have one for the ASM that just got announced. And they say the purpose of the certification program is to independently verify the performance of auto scoring systems. And then to obtain certification, essentially a software must essentially show that it's as good as human scores, basically, or close to. And they use contracted scores for the scoring, and also some statisticians that are working with the ASM. So what are the steps? So essentially what happens is the vendor will give the program to the ASM. They will then upload it on, the ASM will upload it on their computer. They'll have a video conference with the vendor so that the vendor can say, yes, the program is working as we would like. And then once they get off the call, the ASM people will then test it against their held out data sets, and then see whether or not it does well or not. If it does do well, then essentially they are then qualified to get a pre-certification, which they can then, of course, advertise, and they can help them move forward. And they're actually, the submission dates, the ASM is accepting applications near the end of 2022 or beginning of 2023. Applications will be accepted through December 31st of 2023. So what is our part in all of this? So in terms of the sleep ISR, you could, if you have a lab or you are the administrator of a lab, you have to give your users access to actually submit to the ISR. And so, and then the users just have to, that if it is then permitted by the administrator, then the users can then go to the reward program part to actually upload studies, and they can earn points in doing so, and they can earn things like Amazon cards and other various gifts. And so one of the big things is that, what is our part in this? And one of the things to know is that there are many things that we can think about, but the big thing is that we as clinicians are people who are in the trenches. We kind of know this stuff better than anybody else. And we need to be willing to give feedback to these AI programs that we're working with so that they can learn how better to match the algorithm. Because ultimately, these algorithms don't know anything. This is a picture of salmon swimming in their natural environment, but this is actually a picture generated by AI, for example. It doesn't know any better, but is it wrong? Maybe, but that's where somebody who knows the information needs to be able to. And so it's important for us as providers to start contributing our own knowledge to help to refine the software so that we don't end up with fish fillets being mistaken for whole fish. So in conclusion, technology continually follows Moore's law and is reaching levels of human capability. Artificial intelligence may prove a useful tool as we enter the age of big data. Sleep medicine is well positioned to take advantage of the recent advances in AI. Though there is promise, most efforts are still in their infancy. AI may prove useful in incorporating consumer sleep technology into the management of sleep patients. The implementation of AI into clinical practice will require careful consideration and management in order to enhance and not burden the clinical care providers. And so here are some of my sources and questions.